Welcome back to Journeys to the Ice, the podcast of the Antarctic Research Centre. I'm Matthew Wood. This week on the podcast,
I think part of what drew me to it was that I was always interested in the bigger picture. I wanted to know about back arc basins and subduction zones and the really big stuff.
Dhiresh Hansaraj made a significant contribution to the ANDRILL program with his master's research on the acquisition, processing and interpretation of seismic reflection data from the sedimentary sequence beneath the McMurdo Ice Shelf. This geophysical remote sensing technique was integral to both determining the optimal location for drilling and subsequently to tie the major lithological boundaries directly observable in the retrieved core to identified regional seismic reflectors. Following his studies and with a dearth of appropriate career work here in Wellington, he took the opportunity to make his own way in the industry. I caught up with Dhiresh last week in Lower Hutt at the offices of his up-and-coming seismic processing house, Mountain Seismic. Well, welcome, Dhiresh. Thanks for taking time out of your workday to be on the podcast today.
That's all right, Matt. Thanks for having me.
So today we're going to take a look at your involvement with the ANDRILL program through your master's research. Now, you spent 2 field seasons on the ice, is that right?
That's right, yeah.
So during the first of those seasons, ANDRILL was still in the pre-drilling reconnaissance phase of the McMurdo Ice Shelf project. So what sort of work did your initial role involve?
So in that summer season, 2005-2006, we went down to do the last bit of site surveying. So there were already 4 seismic lines that existed leading up to ANDRILL, the MIS project that I worked on. The 3 that I collected were just to round out the seismic grid and get a little more coverage of where the sediments were preserved. So it was all really just to get the best location to drill.
When it comes to drilling a sedimentary record like this, especially in Antarctica, the cost can be astronomical, and so as you point out in your thesis, you really need to choose your location wisely. A site with a thick sedimentary sequence with as few major unconformities or structural complications as possible. Could you explain in layman's terms the geophysical technique of multichannel seismic, which you use to help choose the drill site, and any strengths and weaknesses it has in this Antarctic context?
Well, multi-channel seismic as opposed to single channel, which is how it all started, it's just using as many traces as you can afford. There's different setups that you can use, but it's most common for land seismic surveying. In Antarctica, it's a bit of an interesting situation because you're on a land, so to speak, platform, but collecting technically marine seismic data. So it makes it difficult because of that ice layer. It's on ice seismic as opposed to land or marine. It's sort of in between. What it entails is mechanically generated sound waves, seismic waves, that you direct into the earth in the area you want to examine. And as the waves propagate through the earth, some of them reflect back off the different subsurface layers. And those layers have different properties. The time it takes for the wave to go from the surface, so from the source, which in this case was an explosive source. So the time it takes for the wave to travel from the source down through the ice, down through the seafloor to the layers and reflect back up is recorded on the surface with very sensitive equipment. And we use that to create an image of the subsurface. It's called seismic, and a lot of people think of earthquakes when they hear seismic because it uses the same properties. It's still seismic waves just like those released from an earthquake, except that we make our own and direct them where we want to image.
As I understand it, typical on-land seismic has plenty of its own complications when it comes to generating meaningful results from the raw data. Did you find that working from an ice shelf platform compounded those complications?
Yeah, there were definitely more challenges with ice data because of the ice and seawater, trying to get the energy down to the layers so that they can reflect back was, I guess, one of the challenges. So dynamite explosives rather, were always going to be the best option for us. This survey, like most surveys, is seismic reflection surveying as opposed to seismic refraction. So the seismic waves here reflect off a layer instead of refracting along that layer and then coming back up to the surface. And it was better for a few reasons. It needs less energy than a refraction survey would. It has better lateral resolution, and with refraction, If you wanted to see 1 kilometer deep, you need to have 5 kilometer wide line on the surface. Whereas it's a lot easier to see deeper with a shorter line with reflection.
So the drill site that was ultimately chosen was very close to Scott Base, but it obviously wasn't just this logistical convenience that the decision was based on. What was it about the geological setting of the location that made it ideal for drilling?
The McMurdo Ice Shelf project was the first of the ANDRILL projects, and it was focused on the McMurdo Sound region, where there have been other drilling projects in the past. So based on those other drilling projects, we already had a fair deal of information about that area. And the reason why that area is so special is because it samples 3 different environments. It samples the Ross Ice Shelf, the East Antarctic Ice Sheet, and the West Antarctic Ice Sheet. The location that was eventually chosen and the core was recovered from, I found it amazing. It really had to do with preservation. There's been lots of sediments over the millions of years in Antarctica, but whether it's still there now is really the question. And for the most time, the answer is no, it's not still there. It's been eroded away. It just hasn't been preserved with the coming and going of ice sheets. We were lucky with this in that it was preserved because Ross Island has been loaded by the Ross Island volcanic complex, which consists of 3 volcanoes, Mount Bird, Mount Terror, and Mount Erebus. And because of this loading, there's a flexure on the lithosphere, and it's actually caused a depression into which sediments have infilled. And because they've had a healthy supply of sediment from the Transantarctic Mountains, and they just infill what's been described as a subcircular flexural moat. You can imagine these 3 volcanoes, they're quite heavy, and they're just depressing the lithosphere, and the sediments are preserved from the erosive effects of the waxing and waning of ice sheets.
So that explains the story back to about 5 million years ago when the volcanics were in place. And then you point out that there's this longer-term tectonic history of the area that provided accommodation space for sediments in the Victoria Land Basin as the wider region extended across the Terror Rift system. And so the core that was drilled samples rock deposited up to about 14 million years ago, which was a fairly significant scientific achievement.
Yeah, the McMurdo Ice Shelf project was cutting-edge science. I was very grateful to be part of that and be at the forefront when it was happening, because it kind of was history in the making. The MIS and 1B drill hole has a 98% recovery. It represents the longest continuous drill core of sediments that ever recovered in Antarctica, and was quite the engineering feat because it was from an ice shelf platform, which was roughly 80 to 90 meters thick. And once you got through that ice shelf was 900 meters before you reached the seafloor, and then the drill almost 1.3 kilometers into the seafloor. So it was a huge feat.
So coming back now to your seismic reflection work, in the extended field area, you identified these 6 major reflectors within the sequence that was sampled by coring, and then many other second-order reflectors on top of those. Were you able to relate these seismic reflectors to real lithological features in the core?
What I consider to be my real contribution to the project, and what I found most interesting, was the well tie. Actual hard lithology, the core, always will trump seismic, because you can actually see it and hold it and date it and run a whole host of different physical property tests on it and get real information out of it. So that was always going to be better than seismic. That was never really questionable. Seismic was always to do the legwork, to find the best place to drill, and then once we drill, we have good hard core. The well tie that I did was the most important thing because it allowed a tie between the layers we could literally see in the core to what we could see on the seismic. The 6 reflectors that you've mentioned, they had been identified many, many years ago by various scientists from all different parts of the Ross Sea, and it was no surprise that they were here as well. It's just that we were able to get dates to them now because we actually had core that sampled them. But what was important here with the well tie was that from the well site, we could tie those layers quite well and move laterally away from the well site, but more specifically to move out towards the Ross Sea, where an extensive marine seismic database already exists. It's all well and good having core, but really all we have is hard evidence for that specific location. Being able to tell whether that reflector at 500 meters depth into the core goes out for another K and then just disappears or pinches out, or whether it keeps going is important, because that's how we can get a more wide-reaching story of what's happening in that area.
So you have ground truth, as it were, in a single location, but then through integration with seismic profiles, you're able to extrapolate that geology with reasonable certainty across the wider area.
Yeah, the core at its deepest was 13.8 million. And in that time, the different layers sample the volcanic formation of Ross Island, the tectonic as well as cryospheric evolution of that whole area. So the main reflectors sampled those, but what was the most exciting thing, I guess, was how we could literally see glacial conditions and open marine conditions, so interglacials, in the core. There were over 50 cycles of advance and retreat of the ice sheets. The resolution on seismic is never anywhere near what you can see in the actual core, but I was able to map 17 new reflectors that weren't previously seen and tie them to what we could see in the core and map those out away from the drill site.
So really it's just a fantastic record of the fluctuating grounding line of the ice sheet. In the modern day, there's an ice shelf over the drill site, but periodically there's been a grounded ice sheet and then also completely open water conditions. There's a couple of thick diatomite sections of the core which suggest very little sea ice in the area, which would have to require summer temperatures to be considerably warmer than they are today. And I guess that's really one of the significant findings of ANDRILL so far.
Exactly. One of the taglines of ANDRILL was drilling back to the future, because the goal was to drill back to a time when atmospheric conditions were similar in regards to greenhouse gases to what we have currently, and be able to gauge what we're heading into.
So the goal of your first season was to use seismic to help choose the drill site. And then in your second season, after the hole had been drilled, you and your team conducted what's called a downhole survey, basically using a wireline system to lower various instruments to measure geophysical properties down the hole. Could you talk briefly about the second season's geophysical fieldwork and how these quantitative numerical measurements complemented the more descriptive studies of the core?
Downhole logging and physical properties involved using many different tools, gamma, radiation, calipers, just to measure, I guess, in situ information. The core, when it's recovered, will tell you a lot. It's probably of more use for actual logging, lithology, looking at stratigraphy, even paleomagnetics. But once it is brought up, certain properties do change. For example, wet bulk density of the core. As it reaches the surface, its properties are actually different to what it would be in situ. So we had a whole host of different instruments. More specifically, I was there to conduct a vertical seismic profile, which meant that we dropped a hydrophone down the hole and set off explosive sources again. But this time, having the geophone in the hole meant that it could record both downgoing and upgoing waves, and would provide a better, higher resolution image at the drill site for the main purpose of helping with the well tie. You want the imaging at the well site to be as clear as possible so that you can match that layer in the core at 200 meters to that layer in the seismic at whatever travel time it was.
And the initial science report from that season's fieldwork points out that objectively measured numerical data sets like these really lend themselves to spectral analysis, which of course is great for a scenario like this where you're studying the natural, regular oscillations of the ice sheets. Now, some listeners of this podcast may be earth science students wondering what to specialize in. I know when I was in my third year, I still didn't know which field I wanted to focus on. How did your studies influence what you've ended up doing as a career?
I took an interest in geophysics in second year while at university, and the plan was to do a master's in geophysics and then move into actively working in the industry, specifically seismic processing. I wanted to do that here at home in Wellington, and when I started looking, there was nothing available. So that led on to what started off as just a passing comment at the pub with my good friend Chris, who also studied in Victoria, about starting our own seismic processing house. And he took to the idea and passed it on to his friend Damon, who provided the capital for us to get started. So as of late last year, we formed Black Mountain Seismic and are a New Zealand-based seismic processing house using New Zealand-made software. I'm sure that there are students who are interested in geophysical exploration, and maybe going over to Canada or Norway or London isn't on the cards right now, and they would prefer to get a year or two worth of experience at home, which works perfectly for us because we'd like that as well. We'd like for them to move in and get a little bit of training and experience with us before they moved on to whatever they needed to do. It is still early days for us, but by all rights, I think we're doing quite well. Yeah, it's just exciting times.
And what was it about seismic work in particular that captured your attention, do you think? I only asked because I remember how much fun it was playing with explosives during those undergraduate tutorial sessions.
Well, the explosives were sort of secondary to anything else. They were a sort of added bonus to getting involved in geophysics. I think part of what drew me to it was that I knew relatively early on that I didn't want to look down a microscope for hours on end. I was always interested in the bigger picture. I wanted to know about back arc basins and subduction zones and the really big stuff as far as geology goes, plate tectonics, all of those sorts of things. I think that's why I like seismic processing specifically as far as geophysical exploration goes, because you could also do magnetics or gravity measurements. But I like seismic because it's both geology and geophysics. You have to know some physics and wave theory, but without a geological background, you will not get the best and the most accurate result.
And obviously, having the opportunity to do the work that you love in a place like Antarctica must have been a real blessing.
Exactly. It was incredible, and I'm still very grateful for it.
For more journeys to the ice, visit sciblogs.co.nz/journeys to the ice.